Okay, the second part of this chapter deals with stoichiometry. And so we're going back to the mole-to-mole ratios and such. So we're going to look at gas stoichiometry worksheet number 1, and we're going to look at number 1. So the first thing on part A, we got to come up with a balanced equation. And it tells us that calcium carbonate, solid, which is important, decomposes to calcium oxide, solid, and a gas. So we're going to write the equation. Carbonate is one of those ions. We're going to put it with calcium. So we got Ca, which is in group 2A, and so it's going to be a +2 charge. Put together with carbonate, which again is one of those polyatomic ions on your sheet, which is CO3, and that is a -2 charge. So if they're both the same charges, they just cancel out. So CaCO3 is calcium carbonate. It is a solid. I'm going to put an S behind it. That decomposes, so there's no other reactant. The products are calcium oxide, so calcium is a +2 again. Oxide is just O. It's oxygen with a charge. Oxygen is in group 6A, and so its charge is -2. Again, charges cancel out, +2, -2. We're not going to cross them. They just cancel out. That is also a solid, so we're going to put an S behind it. And carbon dioxide gas. C, di means 2, so O2, CO2. And we're going to put a G after it. Alright, make sure that is balanced before we continue. So count up the atoms on each side. 1 calcium, good. 1 carbon, good. 3 oxygen, we're balanced. So the ratios here are 1 mole of CaCO3 forms 1 mole of CaO and 1 mole of CO2. Okay, the rest of the parts go off of that balanced equation, so we'll kind of come back to that balanced equation as we look at these problems. Letter B, how many liters of gas? So when it talks about the gas, we're looking specifically at CO2 because that's the only gas in the problem. At STP, so we got our temperature is 273 Kelvin, and we got our pressure is 1 atmosphere. And we're decomposing 10 grams of calcium carbonate. Go back to the equation. Calcium carbonate is a solid. We cannot use a gas law for a solid. Okay, so the gas laws only work for gases. That's why they're called gas laws. So if we start with 10 grams of calcium carbonate, which is a solid, the first thing we're going to have to do, if we go back to this equation up here, we have 10 grams up here of this. We need to convert the grams of this to moles of this, because we have to go from the solid back to the gas. And so we're going to do some stoichiometry. Remember, when stoichiometry, we always start off with what we're given, 10 grams, and we're going to write calcium carbonate after that. So 10 grams of CaCO3. When we do stoichiometry, we kind of do the railroad tracks. We go from grams. The first step is always go from grams back to moles. So grams to moles. And this is still CaCO3 in both steps. Alright, so we need the molar mass. And the molar mass of CaCO3, I'm not going to do the math there. You're going to add up the calcium, which is 40.08, I believe, plus carbon, which is 12.01, and there's 3 oxygens, so that's 3 times 16. Add all those together, and you get the molar mass. And remember, on the periodic table, we're rounding to 2 decimal places. So when I add all those together, I get 100.09. 100.09. I'm in moles of calcium carbonate. I don't want the solid. Again, I want to go to the gas. So I'm going to do one more step here. I'm going to put the moles of CaCO3 down here so it will cancel out. And I'm going to go to the gas, which is CO2. The mole-to-mole ratio, this is where I look at the coefficients. So I go back to my balanced equation, and the coefficients are, there's a 1 here, obviously, and a 1 here. That's not always the case, so go make this step right here is where you look at the coefficients, but both the coefficients are 1. So all the units cancel out, except what I'm looking for, which is moles of CO2. When you do the math, It's basically just 10 divided by 100.09. And we started off with 3 significant figures here. So I'm going to end up with 3 significant figures. All right, so this is how much CO2 I have. Now again, this is a gas, and when we were doing the gas laws, the symbol that we used for moles was N, going back to the ideal gas law. Okay, so now we know N, but we know N for the gas. Make sure we know N for the gas, not the moles of the solid, but the moles of the gas. All right, so let's go back to, if we're looking for liters, let's go back to the ideal gas law. Here's the ideal gas law. But I want volume. And again, I always rearrange this equation. So if I want volume, I would rearrange it to look like this. So N, again, whenever you use a gas law, you have to use the gas. So the only gas in our equation was CO2. So make sure when I use these numbers, I'm using the numbers for CO2, because that's the gas. So when I use N, I'm using the moles of CO2. Which we just found. R is the constant. Temperature, it's at STP. So standard temperature is 0 degrees Celsius, but we are in Kelvin. So 273 Kelvin. But that comes from the STP right here. And then P is pressure, but standard pressure is 1 atmosphere or 760 millimeters. But we have to use atmosphere. So anytime we're using the ideal gas law, we have to use ATM. So to find the volume of the gas, I need the moles of the gas, I need the temperature of the gas, I need the pressure of the gas. So when I solve that, I will get the volume of the gas, which is 2.24 liters of CO2. So this was a stoichiometry problem first, and then a gas law problem. So stoichiometry and then ideal gas law. All right, so look at part C, and then I'll kind of skip down towards the bottom. How many liters of gas? We're changing the temperature. We're changing the pressure. We're still looking for liters. Question over here, did moles change? Well, it doesn't say anything about the moles changing, so no, we're going to use the same amount of moles we got up here because it doesn't say the amount of gas changed. So pressure, and again, because it's collected over water, this is the total pressure. But this is Dalton's law. So I would take 823, I would subtract the pressure of water. And to find that, you go back to this chart right here, which you should have in your notes from last chapter. I would find 26 degrees Celsius right here, and the pressure at 26 degrees Celsius is 25.2. So I'd take the 823, I would subtract the 25.2 to get the pressure that I would use in this particular problem. So the pressure I would use is 798. And when you subtract and you look at sig figs, you look at decimal places. So since this does not have any decimal places, I rounded my pressure off over here to no decimal places. So when you subtract, you look at the least amount of decimals. This doesn't have any. My answer doesn't have any. But once you do that, once you find the pressure, then you would do the same equation in RT over P. Just use this pressure. Okay, I'll let you work through that one. Let's go down to letter E. Letter E. Now, E and F are going to be worked pretty much the same way. They're going to be kind of worked backwards of what we did previously. Okay, so how many grams of the carbonates, in other words, how many grams of the CaCO3 are needed if we have this volume of gas at STP, so standard temperature, standard pressure. So we have a volume of the gas, which is CO2. We have a temperature, and we have a pressure right there. So when I say work backwards, we're going to start with the gas law. We're not going to start with stoichiometry. We're going to start with the gas law and then use stoichiometry. So in other words, let's do PV equals nRT. Let's do this first. I know the pressure, I know the volume, I know the temperature, and of course I know R. So I'm going to solve for N. I'm going to solve for N. I like to rearrange it, so I will say N equals PV over RT. So for the gas, again, this is for CO2 because this is the only gas in our problem. So we're solving for N of CO2. Pressure, well, it's standard pressure right here, which is 1 atmosphere. Volume, it tells me the volume, 10 liters. R, constant. And temperature, it's standard temperature, which is 273 Kelvin. So when I solve this, the PV over RT, I'm going to get 0.446 moles. And again, with sig figs, I only had one number here. It had 3 sig figs, so my answer is going to have 3 sig figs. The 1 atmosphere, that's an exact number. That's 1.00 repeating. The 273 is an exact number also. So we're going to say 273.00 repeating. So if I start with 3 sig figs, my answer is going to have 3. Now this is moles not of the carbonate. This is moles of the gas, which again is CO2. Alright, so I found the moles of the gas, and I want to find the carbonate, which is the CaCO3. So now I'm going to do the stoichiometry. That's why I say it's backwards, because if you go back up to letter B, we did the stoichiometry first. Well, here we're doing the stoichiometry second. So, 0.446 moles of CO2. If I'm already in moles, I'm going to do the mole ratio. I'm going to convert from my gas back to what I'm looking for, which is CaCO3. So I'm already in moles, do your mole ratio. I don't need to convert to grams here, because if I convert to grams, that won't get me anywhere. So moles, do your mole to mole ratio. The mole to mole ratio is the balanced equation, the coefficients. So go back to the equation at the top. The coefficients are 1 and 1. Now that's not always the case, because again, when you look at problems, it's not always going to be 1 here and 1 here. So pay attention to the balanced equation. That'll tell you what to put in this mole ratio. And since I want grams of the CaCO3, I'm going to add one more step, because if I stop here, I've got moles. I don't want moles, I want grams. So add one more step. From moles back to grams. Molar mass is CaCO3. I did it in the previous problem, letter B. The molar mass is 100.09. But again, you get that from adding calcium plus carbon plus 3 oxygen. So these stoichiometry problems, they incorporate 2 things. They incorporate the gas law with stoichiometry. I know it's been a while since we've done this stuff, but most people did pretty well with this stoichiometry. So it's just kind of refreshing your memory on this, adding that to the ideal gas law. So when I multiply those together, again, I start with 3 sig figs. I'm going to end with 3 sig figs. And that's how many grams of CaCO3 there are. So the important thing with these, with any of these stoichiometry problems is whenever you're doing a gas law, whenever you're doing this particular law right here, you need to make sure that you are in fact dealing with the gas in the problem. You cannot use this for the solid. I know that sounds rather simple, but do not use this for the solid. Use this only for gases.